Okay, as I mentioned when we started biochemistry, that there are basically four major categories of biochemical compounds. Carbohydrates, which is saccharides, mono, di, and polysaccharides are carbohydrates. Protein, which we studied on Wednesday, amino acids are the building block. Proteins, we're going to come back to them on chapter 19 and when we look at enzymes. So we're kind of sandwiching lipids between our proteins, between proteins in general and enzymes in particular. In the middle we had this third major class, lipids. And lipids, saccharides have something really kind of in common. They have a pretty common structure. They all have OHs and a carbonyl. Amino acids, pretty common structure. Those alpha amino acid, 20 different amino acids. They just have different R groups on them, and then how they get pieced together. Lipids are a little bit more diverse group of molecules. Basically, what are lipids? They are all these biologically active molecules that are not soluble in water. Their key defining similarity is that they're not soluble in water. They're nonpolar. These are nonpolar molecules, all right? And so we're going to look at a bunch of them, and we're going to spend a good bit of time looking at triglycerides and what the building block is for the triglyceride. And then I'm going to come back and say, okay, this is how this one differs from triglycerides and maybe how it might be a little bit similar. And then there are going to be some, like steroids, that are just completely different from triglycerides. So we'll make as many comparisons as we can, but just get used to it. I'll show you a slide here that kind of tries to organize these lipids, and maybe it's something you can hang your hat on from time to time. Biological functional lipids as an energy source. Lipids actually have more energy content than the carbohydrates do. So coconut oil, and don't get all scared about calories. You folks need some calories. It takes 1,800, 2,000 calories a day just to keep your body temperature where it needs to be. Because your body temperature is about 20 degrees higher than room temperature. How do you do that? You're burning stuff all the time. You're burning calories. Okay, so I think we get so bent out of shape over diets. We send people off over some sort of fad, and you get fat out of your diet. And what are you doing? You're starving your brain, getting fat out of your diet. We're going to talk about fat, and you're going to see there's a lot of good qualities about fat. That's the other term for lipids. We're talking about fat in the biological system. An energy source, triglycerides, steroids, phosphoglycerides, sphingolipids. Steroids are structural components in the cell membrane. Steroids are critical intercellular messengers. Lipid-soluble vitamins, so there are fat-soluble vitamins. A, E, D, and K are fat-soluble vitamins. Contrary to something like vitamin C, other vitamins that are water soluble. And you need a certain amount of fat in your diet to absorb the fat your body needs. So even like these fat-soluble vitamins will absorb into your body better when there's a little bit of fat in your diet. I'm not trying to fatten all you up. I'm just trying to give you the balanced view of things. Don't get caught on too far at the end of the spectrum. You're probably starving yourself for some things that you need. Okay, here's here's a kind of a good summary slide, and it's almost, we should almost have this about every 4 or 5 slides so that I can come back and say, here's where we are. So in this broad category of everything that's not soluble in water, lipids, we have saponifiable lipids. Now, you should relate to this word a little bit, saponification. That's the reaction of a base with a ester. And that is where this word is coming from. Saponifiable. So you're going to see where triglycerides are saponifiable. These are esters. And they are the simple saponifiable lipids. You're going to see those and say, well, that's complicated enough. But these are simple. And then from there, we're going to get a little bit more complex. The next one we'll look at is phosphoglycerides. And there's a lot of similarity between these two, but one key difference. Okay? So pay attention to this. When you understand this, you'll be able to transfer over to here to see how phosphoglycerides are quite similar, but have a key difference. There's a phosphate ester involved here. But these are all saponifiable. Waxes we'll just mention for about 2 minutes at the most, like beeswax. It is saponifiable. And then over here we have sphingolipids. These two categories are really important and the main components of cell membranes. Every cell of your body, the 3 to 10 trillion cells that are in your body, it's in the trillions, and I don't know if it's 3, 4, 5, 6, or 7 trillion. Every cell has a membrane around it, and it is a lipid layer, a bilipid layer of molecules that protects every cell of your body. So do you need lipids in your diet? Yeah, definitely do. Sphingolipids are coming. These are in your nerve cells, and these are in all the other cells of your body. So nerve cells have this kind of lipid as a cell membrane, and phosphoglycerides have that kind of lipid in the cell membrane. Okay, then there's non-saponifiable, and the main thing we'll talk about here is steroids, and we'll see the different structure. Okay? So get that kind of a little imprinted in your mind, whether I can fade back to it or not. It's kind of the map to show you where we are on this journey through lipids. All right, so here's where we want to start. Triglycerides, and we're going to go one step below that. What are they made out of? What are they made out of? And you're going to see that you've already heard about these fatty acids. So remember your old friends, oleic and stearic acid. Okay? Oleic and stearic acid from chapter 14. Long chain fatty acid. We use those as an example. You have formic acid and acetic acid and butyric acid. And then I said, okay, there's oleic and stearic. Stearic is saturated, oleic is unsaturated. That's what we're talking about. Those kind of long-chain fatty acids are the building blocks for triglycerides. So let's just remind ourselves and maybe go in a little bit more depth on these fatty acids. So they have a long nonpolar tail, and they have a carboxylic acid group on one end of it. The nonpolar tail is what makes them a lipid. They are not soluble in water, even though one end of it is very polar. The carboxylic acid end is very polar. The overall molecule is not going to dissolve in water. All right, so we only talked about oleic and stearic, but now we want to kind of broaden that out. The most common chain ranges are 10 to 20 carbons long. Oleic and stearic, remember how many carbons? How many carbons in stearic acid? 18. That's an even number. Usually an even number of carbons. So they're like 10, 12, 14, 16, 18, 20. They can be a little bit longer, 22, 24. There's a, oh, am I going to remember the name? There's a movie. Oh, what is the name of that movie? It's about a little boy with a genetic disease. Oh, I can't remember his name. It's called, this is a true story. Oh, I have to remember it. It's a, anybody have any idea what? Well, the condition was when he was about 8 or 9 years old, it developed that he couldn't metabolize a certain fatty acid in his diet. And it's an unusual name for a boy. Not real unusual, but I'll think about it. Lorenzo's oil. That's it. Lorenzo. Is that it? Lorenzo's oil. This is a beautiful story, and it really relates to this.
My mom is a nurse, and her home health care patient has that.
Right now? Is that right? Okay. Lorenzo's oil. The beauty of this story is this little boy, perfect little boy, just growing up, happy. He gets to be about 8 years old, and his development starts declining, and the parents are beside themselves trying to figure out what's wrong with Lorenzo. The father, who knew nothing about chemistry, he ends up getting an honorary degree, I think, in biochemistry, because he sorted this thing out. And this is back in, I don't know, 1960s and 70s, something like that. It's fairly, I mean, it is a true story. But it made me think of it because his condition was with a fatty acid that I think is like 22, 24 carbons long, a little bit longer than this. I would recommend the story, that you might even get a little bit of biochemistry in there. But the father ends up, I mean, hours and hours and hours in the library studying papers on anything that relates to this, and he solved this problem. He solved this problem. It's a beautiful story.
Did you have to get the medication like within a certain time?
Yes, this is a problem with Lorenzo, and in the movie they say, did we help everybody else's child? And the answer to that question is yes. It took a couple years to figure this whole thing out, and during that whole period of time, Lorenzo is declining. But they do finally arrest the decline. They are able to solve it well enough to arrest the decline. But if it's found early enough, you can actually avoid the decline. I want to talk to you more about what your mother is doing. Okay, nonpolar tail, responsible for the characteristics of the fat. It's the carboxyl group. It exists as the carboxylate anion. So you're hearing this is the carboxylic acid group. Here's your carboxylate. What's that mean? At a pH of 7.4 and above, that's the pH of blood plasma, not of every part of your body, but of the blood plasma. 7.4, that hydrogen comes off, and that carboxylic acid is the carboxylate. You saw that with the glutamate, glutamic acid. So when I say glutamic acid, I'm talking about the acid form, and glutamate, I'm talking about just the dissociated or hydrolyzed form of it. All right, as we learned with oleic and stearic acid, they can be saturated, stearic, or unsaturated, oleic, or polyunsaturated. Omega-3 fatty acids are polyunsaturated and more than one double bond in them. All right, here's our two good friends. You should know these. Know these structures. Stearic, oleic. Here's your unsaturation. It's right in the middle. You know, you could draw this as a CH3 You got 7 CH2s here. You got a double bond. You got another 7 CH2s, 7 of them, and you got a carboxyl group. That's your oleic acid. The double bond is right in the middle. That's important. The way this stuff has been designed is amazing. Saturated, unsaturated. The unsaturation is always the cis configuration of the double bond. In nature, that's what you're going to see. You're going to see a cis double bond. This is why you want no trans fats. All right, trans fats are not a product of nature. They're a product of something we have done to that, either in cooking or in food processing. In the food processing, food preparation arena, we'll talk a little bit more about that. We create trans fats, and those are unnatural, and the body doesn't really know what to do with trans fats, and we probably still don't know what the body is doing with them. Probably still more to learn about them, so better to stay away from them. Fatty acid properties. Some of this is redundant. Straight chain, 10 to 20 even numbers. Okay, melting point increases with increasing carbon number. Yeah, we didn't get into this in chapter 14, so this is fascinating. We're going to wrap our minds around this and try to understand this. The bigger the carboxylic acid, the higher the melting point is going to be. The melting point of a saturated fatty acid is higher than an unsaturated one. Okay, so let's take a coconut oil. Is that a liquid or solid at room temperature? Solid. It is a saturated fatty acid, predominantly saturated fatty acid. So it has a higher melting point than olive oil. What do we say? Olive oil. We say coconut oil, but coconut oil is really not a liquid. We usually use the word oil for liquids, and what do we use it for non-liquids? Like lard or something like that. We call it a fat. Butter, we wouldn't refer to that as an oil. We say it's a fat. It's solid at room temperature. Coconut oil is solid at room temperature. What we're going to find out here is that putting a double bond in the molecule, even two molecules of the same size, you put a double bond in it, it lowers the melting point.
You said when you put a double bond?
Yeah, when you have some unsaturation, like here, all right, so oleic acid has a lower melting point than stearic acid. Stearic acid is the fat that comes from beef, which is what is predominantly stearic acid, is a solid at room temperature. But oleic acid, this is a component of olive oil, is a liquid at room temperature. So, and why? Because that double bond. And we won't dwell on it, but it says right here, the cis double bond prevents good alignment of the molecules, and because they don't align as well, they don't fall into a solid structure. This is what's happening when something solidifies. It's falling into a solid structure. So double bonds lower the melting point relative to the saturated fatty acids. Here's a little bit of the shape. So here might be stearic acid, oleic acid. You can see the cis bond makes it a kink, more like a boomerang, dog leg if you're talking to a golfer. That would be a hole with a dog leg on it. All right. So it's got a bend in it, or a kink. Now, notice, let's compare the cis with the trans. Here's the cis with the kink in it. You got half of the molecule come along here, comes into one side of the double bond, goes out the same side of the double bond, and you got this kink in the molecule. Now, same molecule, this would be the unnatural version of it. You're coming along here, you come in one side of the double bond, go out the other side, trans, isomer. And can you see, keep that in mind right now, that doesn't vary a great deal from the shape of a saturated fatty acid. So you take an unsaturated, you put a trans double bond in it, and it ends up with about the same shape as the saturated fatty acid. Okay, you're still sitting there thinking, big deal. I don't think my body notices. Yes, it does. Okay, we'll get to the end slides, and when we talk about cell membranes, your cell membranes are looking for this kind of a shape. And we won't drill down exactly the detail as to why that is, but that is the shape that serves the cell membrane formation and the getting of the proteins and other things that need to be in there. And this shape doesn't serve that purpose as well. Okay, how do these things behave? This is your carboxyl end of your fatty acid. Here's your nonpolar chain. And if you throw this into water, this is going to present itself to the aqueous environment. It is hydrophilic, water-loving, and these chains are hydrophobic. They want to get away from the polar environment of the water, so they create their own, together create their own non-polar environment. And you have what we call a micelle, tiny little droplet floating around in water. It can be suspended in water there, this tiny, tiny little droplet. And you can dissolve fats inside this micelle. There's a non-polar environment there that can exist now in a polar water environment by the way these molecules operate. They have this dual nature. One end of it is polar, one end of it is non-polar, and they can do this. And this is what soap is. So soap bubbles floating around in water. You've got these kinds of molecules functioning as a surfactant, and they can dissolve fat, oils, whatever's on your clothing, can dissolve that in here and carry it away in water. Whereas if you put, if a mechanic puts a shirt in a washing machine without any detergent, comes out, it's still got the oil all over it. The water can't dissolve that oil off the clothing, but a soap molecule can do that. Okay, back to the melting point. Now, can you, Chelsea, can you turn this light off for a minute? Thank you. Okay, let's take a look at this and understand what we got here. We're looking at melting point. Here's temperatures from minus 20 degrees centigrade up to 90 degrees centigrade. This is about room temperature. So when you get above below room temperature, the material is going to be, if its melting point is below this, it's going to be a solid. And above that, it will be a liquid. So this is where if you take coconut oil, that might have a lot of stearic acid content in it. It has butter with stearic acid from beef fat. There's 75 degrees centigrade. That's high, folks. We're not talking about 75 degrees Fahrenheit. We're talking about approaching the boiling point of water. We're way up there. It is at room temperature. It's very much a solid. You have to get 50 degrees above there for it to melt. Okay, there's stearic acid, 18 carbons long. So that's what we're looking at here is carbon chain length. Short, it's a liquid. 4, 6, 8. You get up to 10, no double bonds, and all of a sudden it's a solid. 12, 14, 16, 18. So now we're at stearic acid. Now, let's put one double bond in there. Boom. Oleic acid. It's 18 carbons long. One double bond, and it's come down to about 15 degrees centigrade. So it is a liquid. At 20 degrees centigrade, it's already melted. 20 degrees is above that melting point. Put two double bonds in it, linoleic acid. And it, bam, it's down here below 0 degrees centigrade, below the freezing point of water. 18 carbons long. It's got essentially the same molecular weight as stearic acid, but a 100 degree lower, almost 100 degree lower melting point. Linolenic acid, 3 double bonds, and it comes down a little bit more, minus 10 degrees centigrade. This is a monounsaturated fatty acid. These are polyunsaturated fatty acids. Omega-3 fatty acids. Are they polyunsaturated? Yes, they are. They're polyunsaturated. I don't know whether they have 3 or 4 double bonds in them. We're talking about this kind of material. Let me ask you a question. If you were a salmon, where do we get our omega-3 fatty acids? I've given it away already. Fish. Fish and maybe some flax. But fish is the major source of polyunsaturated fatty acids that are essential for our diet. I want you to understand why they're coming from fish. If you were a fish and not a cow, cow's a warm-blooded animal. I don't know what their temperature at which they operate, but the cow, even if it's cold out, is burning calories and keeping the body temperature up. But the fish is a cold-blooded animal. The fish's body temperature is the temperature of the water it's swimming around in. And if you're swimming around in a lake that's frozen over and the water is, 0 degrees centigrade in that water, would you want the fatty acids, the triglycerides floating around in your body to still be a liquid? You would. They didn't get the vote on this, but that's the kind of fatty acids they got. They got the kind of fatty acids that do not solidify at those low temperatures. This is where we're getting that in our diet.
So below room temperature is a liquid, right?
Pardon me?
Below room temperature?
Yeah, if the melting point is below room temperature, it's a liquid at room temperature. At room temperature, it would be liquid. Here is the temperature at which it becomes a solid. There's the temperature it becomes a solid. Here's the temperature it becomes a solid. So down here, minus 10 degrees C, that salmon can be floating around in water that's below freezing, 1 or 2 degrees below freezing, and that is still liquid. Those fatty acids are still liquid. So this all makes sense. All right, so there's the linolenic, 1, 2, 3 double bonds in it, 18 carbons long. So there's oleic, monounsaturated, linoleic, 2 double bonds, linolenic. And arachidonic, we'll talk about that. I think we'll talk about that towards the end of things today. So there's some saturated ones. Decanoic, so 10 carbons long. Dodecanoic, 12. Tetradecanoic, 14, 16, 18, 20.
Are there any, fatty acids on that chart that we need to, besides the
Stearic and oleic, you already know. You probably, I don't necessarily expect you to draw the structures of these, but there may be some questions come up that say, name or which one of the following is an essential fatty acid. And a couple of these are essential, meaning our body can't synthesize them. If you don't get them in your diet, you're lacking them. That's why I take a teaspoon of fish oil every morning to get the omega-3 fatty acids. All right, I think this is pretty redundant. Some things we've already mentioned with just some of the same. Well, it's showing the common sources of some of these. Fish oils, fish oil, seafoods. All right, so there's some telling you where you're getting some of these. Stearic, lard, beef fat, butter fat, cottonseed oil. Okay, if you render the fat out of beef fat, you end up with lard. Well, Crisco, years ago, probably early 1900s, said, well, you know what, if we take, so people were kind of used to lard. They'd take lard and they'd melt it down and cook their french fries in it and things like that. Crisco said, you know, we could take corn oil and things like that and hydrogenate it. What are they doing? They're knocking the double bonds out of it. What's that doing? That's raising the melting point. What's that doing? That's making it a solid at room temperature. You could take something that's a liquid at room temperature. Through hydrogenation, you can turn it into a solid. That gave rise to Crisco and margarine and trans fats because of the hydrogenation process. It's isomerizing those cis double bonds. So, I'll pick up something new that I think I might want to buy, and I look at it, and it says partially hydrogenated vegetable oils. I put it back on the shelf. I don't want to buy that. Partially hydrogenated is worse than completely hydrogenated because they have isomerized some of the double bonds and left them in there, and there's going to be some trans fats left around. There might stay on a label, no trans fats, but there's some in there. By law, you can say that if it's less than 0.5 grams. So they can still say no trans fats. So if you look for partially hydrogenated this or partially hydrogenated that, I also think some other labels in there that are pointing to. Why is it?
Where?
Ingredients. Ingredients. If you look under ingredients, it should say that. It might hide it a little bit. It might say modified vegetable oil or something like that. What'd they do to it? They probably hydrogenated it. Okay? They want to, as soon as they know there's someone out there like me who knows what partially hydrogenated means, they try to find another word for it so that it will throw you off a little bit. Okay, let's move on. I'm getting all this on tape. I don't know. Okay, now let's go to triglycerides. When we get to triglycerides, we're looking at the fatty acids as one of the components, and we're going to link that now to a little molecule and make an ester. And we're going to get a triglyceride. A triglyceride. This is giving you a hint of what that little molecule is. Glycerol. We're going to react three fatty acids plus the glycerol, and we're going to get a triglyceride. Triglyceride. It is a triester. It's a molecule that has 3 ester linkages on the same molecule. Let's take a look at it here. Triglyceride. All right, let's zero in on this molecule right here. Here's a fatty acid. Here's a fatty acid. Here's a fatty acid that now has been linked to glycerol, an alcohol. And the linkages, all three of them are esters. You can see the ester linkage that's holding the fatty acid on the glycerol. So, Sylvia and the rest of you, that is a 3x5 card. Know the structure of glycerol. 3 carbons long, and there's an OH on every carbon. It's a triol. We looked at ethylene glycol when we were back in chapter 12. It's a diol. Ethylene glycol, it has an OH on each of 2 carbons. This is an OH on each of 3 carbons. And this is a natural compound. Your body makes this. Your body breaks down triglycerides and it will give off a glycerol molecule. Can reuse that glycerol molecule to build a different triglyceride. All right, so this is a natural component. Here's what it looks like. Here's your glycerol, 1 molecule of glycerol, 3 OHs. Here's your stearic acid. Here it is with 3 molecules of stearic acid. You won't find this in the body or in beef either. You typically do not find, this would be a homotriglyceride where all 3 of the fatty acids are the same. That's not the way nature works. Nature will usually make a triglyceride where all 3 of these are different. It's 3 different fatty acids. Like this. You can see these are different. There's 2 double bonds in this one. I think it even has the names underneath them. This would be stearic acid, this would be linoleic, and this would be palmitic acids here. That's a typical triglyceride. Has 3 different fatty acids on it. But just to simplify things for us to get our minds wrapped around what a triglyceride is, not to complicate it too fast, I'm taking glycerol, reacting it with 3 stearic acids, and you get, you're splitting out this water right here to form this ester. Splitting that water out, getting an ester. Splitting that water out, getting an ester. There's your 3 waters. All right. You remember esterification. Esterification was an alcohol plus a carboxylic acid yields an ester plus water. Well, we're working with the triol. We're going to react 3 carboxylic acids with it. We're going to get a triester and 3 molecules of water. This is an esterification reaction. And let me just take a look at this right here, just so that you see what this looks like. And if that were stearic acid, to simplify this, I'm going to have a CH2. I'm going to have 16 of these and a CH3. All right? So could do that 3 more times over here, or 2 more times. 2 more times right here. But what I just want you to see is the carboxyl end is pointing towards the glycerol, and as you come out to the other end of the tail, it ends with a CH3 group. So this is all, from here over, is your non-polar tail out there. And there's three of them. There's three of these non-polar tails sweeping out here on the triglyceride. And all of your oxygens, your ester linkages and everything are concentrated up here at the glycerol end. You with me? All right? You should be able to duplicate that. If I said draw out the formation of a triglyceride from the reaction of glycerol with 3 stearic acid molecules, that's what it's going to look like. Okay, Deborah? No, but
You just want to
well, I won't say no. Assume you will. Okay, assume you will. And you'll be in better shape. Components. So here it is in a simplified form. We have a glycerol backbone holding 3 fatty acids. Remember that this is all the CH3 ends of the molecules out here. This is all nonpolar, lipid, hydrophobic. There's a little bit of a hydrophilic nature down at this end because there's 6 oxygens down here. 3 ester linkages, 6 oxygens. All right, so that is, I'm going to draw that on the board so that when we get to another topic, you'll be able to see the similarity. So we're going to just say we got our glycerol here. And we got these 3 fatty acids coming off of it. That's your triglyceride. And you'll see it just sometimes just abbreviated as TG, triglyceride. Yeah, like I mentioned, the fatty acids are rarely identical. So it'll be a mixed triglyceride. Mixed meaning different, 3 different fatty acids. Triglycerides from animals other than fish are solids at room temperature. Triglycerides from plants and fish are lipids at room temperature and called oils. So yeah, they're called fats. You say beef fat, you say olive oil. All right, here's a little idea if you just kind of look at some of the differences. Here's olive oil, butter, and beef fat. So yeah, don't buy it if it says it's partially hydrogenated, and don't buy it if it says it's a margarine. Margarine was the food industry's way of trying to mimic butter. If you want butter on your food, buy butter. I can't believe it's not butter. It's not butter. So I can't believe anyone would buy it. It's not butter. Not when you, right next to it is butter. So buy the stuff that's right next to it.
Right.
And put a little sign there. So I can't believe anybody would buy it. All right? Olive oil, butter, beef fat. All right? Don't tell HEB I said this stuff. All right?
So why do they still sell it? I don't get it.
Because people like it to spread on nice and smooth. Keep your butter. Don't put your butter in the refrigerator or something. Take it out earlier. Get it on your toast before it cools down. Do something. All right? This is healthier for you. But here, what are we looking at? So you got 3 colors here. This is a long chain saturated fatty acid, stearic. Think of that as stearic, mostly stearic acid. Here's a long chain unsaturated. Think of that as oleic. And then there are short chain saturated fatty acids. So here's your beef fat. It has a little bit of the short chain. It has some oleic acid and a lot of stearic acid. It's not all stearic acid. It has oleic acid in it. And another fatty acid. This would be the triglycerides that are coming out of beef fat. Mixed. This is what I mean by a mixed triglyceride. Olive oil, let's contrast it there. This is a fat. It's a solid at room temperature. Olive oil, this is a liquid at room temperature. Lot of oleic acid, little bit of stearic acid, a little bit of this shorter chain saturated fatty acid. And every oil you can talk about, palm oil, coconut oil, whatever, you could actually do a deep dive and find out what are the 3 fatty acids in this oil. Corn oil, whatever oil you want to look at. There's a ton of them out there. But this is the kind of thing you would see. What are the fatty acids that are the component? This slide, I need to get that out of there, but I just Googled different cod oil, coconut oil, so I don't remember the titles of these columns, but this is telling you the composition of different fatty acids that are in there. Excuse me. Okay, quickly, let's just mention some reactions. And again, if you went back to chapter 14 when we talked about carboxylic acids and esters, and then we said, okay, what are some of the reactions these things can undergo? You'd get into these 3 reactions. This one would come out of chapter 11, hydrogenation, and this would be the unsaturation in the triglyceride. You're hydrogenating it to make it saturated, and you're going to raise the melting point. Saponification, that's what this is. So I don't know, maybe I could title these. This is hydrogenation. This here is saponification. This is where it gets the name a saponifiable lipid. And this is acid hydrolysis. These are the reactions. Now I got one slide for each one of these. Let's just look at them real quickly. The hydrolysis. This is the acid hydrolysis. So what do we got here? We've got a mixed triglyceride. There's your glycerol backbone with 3 esters coming off of it, 3 ester linkages. There's a saturated, it's got 14, 15, 16 carbons. There's an unsaturated, that would be oleic acid. How do you know? CH2, double bond, CH2, CH3. So there's oleic acid right there. It's monounsaturated. And then you got, this is probably linoleic acid. This is a little bit hard to follow, but there are 2. There's a double bond right there. Let's see if we can make that bigger. But you see there is a double bond right here, but there's 2 of them. There's a parenthesis around this thing with a 2. So there's 2 double bonds in there, 1 double bond in there. 3 different fatty acids. All of those are different. And what do? You take water, and in the presence of an acid, or here they're writing lipase. What is that? Chapter 19. You're going to see these kind of molecules. ASE ending. An enzyme that will break down that triglyceride into glycerol and 3 fatty acids. Okay, so this would be what your body does with a triglyceride. You put olive oil on your salad and you eat it, and your digestive system goes after that and breaks it down into this, and the fatty acids absorbs those into your body and then creates the triglycerides it wants to create out of it. Maybe it doesn't like the triglyceride that comes from beef fat. Doesn't think you're a cow. Wants you to have human triglyceride. So it digests it, rebuilds it on the other side of the intestines or in the cells, rebuild it. So there's acid hydrolysis.
So just to clarify, you said that stearic and oleic are the only 2 so far that we for sure need to know the structure of.
Yeah.
For
Right. And the glycerol, and be able to kind of piece together this general structure. Know that you got, what this thing looks like over here. 3 esters. Saponification. Again, some of this is going back, a throwback to what we learned in chapter 14. Here's your triglyceride. Instead of three water molecules here, this is the reaction with a base, saponification. 3 NaOHs are going to clip these bonds right here. And you're going to get a carboxylate, so sodium palmitate, sodium oleate, sodium linoleate. Hope I don't have to sing a song with that in it. Okay? And these are soaps. This is how you make soap. You saponify the lipids that are in these oils. How do you make soap? You take coconut oil and corn oil and olive oil and saponify it, and you can make soap. So that's saponification. And you get glycerol. So you get an alcohol and the sodium salt of the carboxylic acids. And those are the soap molecules. They have this polar end and non-polar hydrophobic tail, and these function very well as soaps. Okay, finally, hydrogenation. If that's big enough. We've got a double bond here and 2 double bonds down here. This would be the example of partially hydrogenated. So whoever was hydrogenating this, didn't want to get rid of all the double bonds. Why? Because it would have made the melting point way too high. It would be just as hard as the butter. They want something that's a margarine that's nice to spread, so they're getting rid of 2 of the double bonds and leaving one of them in there to get the melting point they want. Okay? Because people were used to butter, and they say, I like this margarine. It's softer. It's softer. And so they figured out just how soft, how hard people wanted stuff, and they made it by hydrogenation. It's a hydrogenation catalyst. I don't know where that ends up. I'm sure they try to get it out of there. It is very low levels. Okay, implications of hydrogenation. It can result in trans fats. Can isomerize the double bond from cis to trans. Saturated fatty acids have been implicated in higher blood cholesterol. And I really think we have to think about this. Is this the saturated ones that occur naturally in the diet, or the saturated ones that occur as a result of hydrogenation? So, because you hear this, that saturated fat's not good for you, and then in the same breath you'll hear coconut oil is pretty good for you, and it's a saturated fat, right? You hear both those things. So, I haven't sorted that one out completely, but I eat coconut oil. And I'm still here. But if anything happens to me, take it out of your diet. Okay, I said we'd spend 2 minutes on waxes. Why are they right here? Well, they have an ester linkage. Well, before I do the waxes, any questions on triglycerides? All right? That's your first major category, and the easiest to wrap your mind around. You can see all the similarities with chapter 14 and saponification and esters, etc. There is some common structure to this. You got a glycerol backbone. Yeah, there's a whole bunch of different fatty acids, but fatty acids have a certain structure, certain number of carbons long, saturated or unsaturated, carboxylic acid functionality. So you can wrap your mind around this. That's your first major category of lipids.
In hydrolysis, you're always going to add 3 of water, right?
For a triglyceride, yes, you need a water for every ester linkage. In chapter 14, we only had one water molecule because we were dealing with something that only had one ester functional group in it. But now we're working with a triglyceride, and there are 3 esters on every molecule. So you need 3 molecules of water, one to hydrolyze each ester. Okay, waxes, very briefly. There's your ester linkage. Waxes, these things are completely insoluble in water. Here's your carboxylic acid reacted with a very long chain. Let's look how long that is. All right, 29 of these, 30 carbon long alcohol. So this is a long chain alcohol reacting with a fairly long chain, 16 carbon long carboxylic acid. You have no hydrogen on this thing. You have a couple oxygens here, but surrounded by all of these 2 very long nonpolar tails. This is what the kind of stuff that beeswax is made out of. I mean, beeswax, you can rain on it for 30 days. It's not going anywhere. It's not going to dissolve in the rain. All right, those bees know what they're doing. Very water insoluble, and that's waxes. Not easily hydrolyzed, very water insoluble. That's waxes. Okay, let's take a 5-minute break and we'll jump over to phosphoglycerides. All right, I started, not triglycerides, phosphoglycerides. Phosphoglycerides. Now, I've started a diagram of it. I want you to see how similar. We've left a little spot off right here. This is what we're going to need to understand, what the phosphoglyceride looks like right here. But right now, I've shown you the similarity. Phosphoglycerides, triglycerides have a glycerol backbone. They both have fatty acids attached to that glycerol backbone. Triglycerides, 3 fatty acids. Phosphoglycerides, 2 fatty acids. This is the major component of the cell membranes, phosphoglycerides. This is what your body uses this for, to build cell membranes. So you have a glycerol. The components of it are glycerol, fatty acid, phosphoric acid with an amino alcohol functional group on there. All right, so this is what that 3rd spot looks like. You have this is a phosphate ester here. So these are esters. Here you're going to have a phosphate ester with an X group of some sort, some different functional group on there. Yeah, so one of the OH groups of the glycerol is joined by an ester linkage to phosphoric acid. So there's your phosphate ester, which in turn is linked to an amino alcohol functional group. All right, here's drilling down into that in a little bit more detail. There's your glycerol backbone one fatty acid, another fatty acid. Here's your phosphate. Here's your phosphoric acid that has gotten reacted on to that OH, that third OH on the glycerol. So it's no longer phosphoric acid. You got this phosphate ester. Here's a carbon-oxygen double bond, a carbon-oxygen-carbon bond, ester. Here's a phosphorus-oxygen double bond, phosphorus-oxygen-carbon bond. It's your phosphate ester. But that phosphate has 4 oxygens around it, and on one of those oxygens is a substituent of some sort. And here are a couple of sorts of X's here. It can be choline. It's an alcohol, 2 carbons, and then you have this quaternary ammonium salt, quaternary ammonium ion here. You see a nitrogen with 1 and 3 methyls, 4 carbons around it. It's a quaternary ammonium functional group there on choline. So what we learned in chapter 15 when we studied amines actually occurs in biological systems. Biological systems use this functionality in phosphoglycerides. Here's ethanolamine, so an OH, 2 carbons, an amine group. Ethanolamine. So this would be this X group. This hydrogen would be off of there. It would be a phosphorus, oxygen, and then this here. This is how it's linked to the phosphate. Serine. So what is serine? Serine is an alcohol functional amino acid. So you take that amino acid and bond it onto that phosphorus group, and you have another phosphoglyceride. So there are varieties of phosphoglycerides according to what X is. All right, now I expect you to kind of appreciate, you know, what we've got here, at least to this extent, to that extent, all right? So don't think I'm going to say draw this phosphoglyceride with these 2 fatty acids, this glycerol, this X group. You don't have to drill down into this far. You need to know some general things. This is a major component of cell membranes. It's similar to triglycerides in many respects, but differs in one very important region right here. I think you should understand this portion of this molecule. You got a carbon-oxygen phosphate ester linkage, and that's about as far. You'll see on the homework I have you draw some things. I give you some questions, some molecules. I'll say draw this steroid, draw this phosphoglyceride, but I don't expect you to memorize that. I know you can go to your book and look at that and draw it, and that's what I do want you to do on some of those homework problems. But that doesn't mean you have to memorize those molecules. So here's phosphatidylcholine. So phosphatidylcholine is the phosphoglyceride with 2 fatty acids and the choline substituent group on. Phosphatidylcholine. You may get into anatomy and physiology, or maybe you already have, and had heard them refer to phosphatidylcholine. I don't know. Cephalins, ethanolamine or serine functional phosphoglycerides found in cell membranes, blood platelets, blood clotting process. Okay, there's phosphoglycerides. Wow. This is moving.
Can you go like up one slide? Because I don't understand that. So you're just taking that alcohol with amine and just plugging it into the X?
Yeah, so let's look at that alcohol. Let's look at this portion of the molecule. So there's your glycerol. And what you would, there might have been an OH here, and then you would have had the H on your ethanolamine, okay? And you're going to get rid of that water molecule. And it's going to bond onto there. So let me erase that. So if you bonded that onto there, you would now have your 2 carbons and your NH3 group. That's what I mean. That's what that X would look like. It's an alcohol functional. X is alcohol functional. Why? So that it can combine with the phosphoric acid by dehydration. It's going to split out a water molecule and form that linkage right there. So this hydrogen is going away. And this ends up being the X that remains. So in each one of these cases, you'd lose this hydrogen, and this would be your X group. Okay?
So I'm just taking the hydrogen out.
Yeah, taking the hydrogen off, because it's going to react. You know, that's how it's going to link up with this group here. There's an oxygen down here. It's going to split that. Well, you can take the hydrogen and oxygen off of there. One of those oxygens has to go, either the one that's on the alcohol amine group or on the phosphoric acid group. But you're going to split out water molecule and link that, combine that to the phosphoric acid, and you have made your phosphoglyceride. Okay, now I said at the beginning to kind of get this slide. I wish I could easily get back to it. This early slide right here. All right, so what have we covered? We've covered this. We've covered a lot here in terms of saponifiable lipids. 2 simple ones. They're ester functional groups only. 1 complex. We got the phosphate ester. So now let's look at sphingolipids. All right, so we're talking about non-glyceride lipids. Now, what do we mean there? We don't have a glycerol group. We don't have the 3-carbon, 3-alcohol functional crosslinker as the backbone of sphingolipids. What do we have? We have sphingosine, which is a little bit more complicated structure than glycerol. You agree? It's a little more complicated than glycerol. All right? You still have 3 carbons. 3 carbons. You do have an OH here. I mean, if you looked at glycerol, you know, there you got that similarity. You move up 1 carbon, you don't have an OH, you have an amine. You move up 1 more carbon and you don't have an OH, you've got a nonpolar chain right here, and even a double bond in there. So you don't have an ester linkage here, you just have a long carbon chain. That's sphingosine. Now if you take sphingosine and move it on down here, And now you take a fatty acid, and you're going to link the fatty acid at this middle carbon. But look, you don't have an ester, you have an amide. Carbon-oxygen double bond on a nitrogen. So you have a little different linkage there. You still have this long chain here, which is nonpolar. This is nonpolar. And then down here you have an X group. The X group's going to come off of this hydrogen here. And you're going to get different kinds of sphingolipids based on what this fatty acid is and what this X is. You vary these two, and you have different sphingolipids. All right, these are they did say these were saponifiable. Yeah, I guess maybe you could react this bond right here. Okay, so they are saying, they're still indicating these in the category of saponifiable lipids.
Do we have to know this?
What?
Bingo. Like the
You don't have to know this structure. What do you need to know?
Probably that's just attached to an amine group, right?
Well, you need to know they're different from phosphoglycerides and what their function is. They're not a glyceride, not a glycerol backboned molecule. Okay, this is a little hint right here, sphingomyelin. The myelin sheath, what is the myelin sheath in the body? Myelin sheath. Where do you find that? Okay, that's the structure around nerve cells, the myelin sheath. These molecules are critical to nerve cell membranes. All right, so sphingomyelin. Let's just look at them a little bit more. Yeah, so just kind of understand where they fit into the lipid scheme of things and what they're used for. Yeah, the myelin sheath feature. See what different R groups are. So sphingomyelin. Here's your amide linkage to a fatty acid. Here's your long carbon chain. It is on the sphingomyelin. And then what is X? Well, you got a phosphate linkage to the bottom carbon, and so this was your choline, your two carbons, and your quaternary ammonium functional group right there. This is what X is. This whole thing right here is X, choline and a phosphoryl group. That's sphingomyelin, used in critical in nerve cell membranes. So this is nerve cell membranes. Phosphoglycerides is so yeah, this where that's triglycerides, phosphoglycerides. Phosphoglycerides are critical to all cell membranes, and sphingolipids are critical to nerve cell membranes. Before I move on, let's just, when I start talking about cell membranes, it will be useful to remember kind of what's going on here, all right? Here's a fatty acid right here, long chain fatty acid, hydrophobic. Here's a long chain of carbon here, hydrophobic. And then what happens from there is as you get up in this region right here, what are you seeing? You're seeing a charge. You got a negatively charged oxygen. You got 4 oxygens. You got another oxygen here, amide linkage. This whole area right here there's a lot of polarity right there. Well, let me not miss this hydroxyl group right there. All right? And then that's right in this region right here. Keep that in mind. Because what we got, I can get rid of this. What we've got is two hydrophobic tails and a head on this molecule, and there's a charge right there. So there's a negative charge there, a positive charge there on the quaternary ammonium structure. So I should draw that all around there. This is polar. And this is all nonpolar. When we start seeing how the cell membrane forms and why it is a good sheath around the cell, this is going to be this and the phosphoglyceride. Phosphoglyceride, we could say the same thing. We could draw a big circle right around here and say we've got a lot of polarity in this region and a lot of nonpolar structure to the molecule in that region. And these are even better than the triglycerides in terms of that feature of them. Because you've got negative charge here, you can have charges out here on the amines. All right, maybe I'll come back and mention that. Types of sphingolipids. Different kinds of R groups. You can see here you got a sugar. We don't have a we don't even have a phosphate on here. We're linking a sugar on here. This is what is that? Glucose? Yeah, glucose cerebroside. And here is I think galactocerebroside. You can see here's galactic acid. Just handed that back to you. Chapter 16. What's the difference between glucose and galactose? This hydroxyl group right here. So here's galactocerebroside, glucose cerebroside for brain cell membranes. And these are sphingolipids. Gangliosides, okay, a whole gang of sugars. 1, 2, 3, 4, 5 sugars hanging off where you'd have X. You've got 5 different, you got a pentasaccharide there. And that's a blood group antigen. Don't worry about the sulfatides. Types of sphingolipids. If X is just a hydrogen, in other words, if that sphingosine just ends up staying as an alcohol functional group down there, there's no X really, it's a ceramide. Then you've got sphingomyelin, that's choline, phosphatidylcholine, neutral glycolipids. Neutral, there's no charge on this, but there's a lot of solubility, a lot of polarity here. So the glucose is very soluble in water. That's a very polar X group. And then some others here, the ganglioside. So types of sphingolipids. And then there are various genetic diseases, like we were talking about with, what's his name again? Lorenzo. Now this isn't one of them, but Lorenzo had a genetic disease, and it only appeared in boys at the age of about 8 or 9 years old. 7, 8, 9 years old. They just moved along just fine until they reached about 8 or 9 years old, and then it started manifesting itself. But here is sphingolipid storage diseases: Tay-Sachs, Gaucher's, Krabs, Niemann-Pick. And what's going on? The lack of a particular enzyme. It is the critical thing here. So genetically, the DNA is not coded to make this particular protein, which is an enzyme. And therefore it can't make the the necessary sphingolipid, and it leads to these various manifestations of the disease. All right, I think that is probably good enough. So we've got triglycerides, phosphoglycerides, sphingolipids, and a kind of an idea of what's going on there. I'm not really sure how the body uses the triglycerides except to, they're in your bloodstream, and if you get a blood analysis, it'll tell you cholesterol levels and triglyceride levels. And what are they? They're carriers of these different fatty acids that your body might need. And I'm not exactly sure what other things they're doing. I'm sure they're doing a lot. But it is a way to get these different fatty acids that these different phosphoglycerides and sphingolipids need. Okay, you ready to shift over now? We're going to move away from saponifiable lipids to steroids now. So the steroids are in a class all by themselves. So there really isn't too much we could say to compare them to these triglycerides and phosphoglycerides, except that they also are not soluble in water. Okay, now pick out a little spot in your notebook, and I want you to draw something. Okay, draw what I draw right now. Start over on the left side, not way over on your margin, but on the left side of your paper. Don't start right in the middle, because we're gonna build this out from left to right. So you know how to make a six-membered ring. So draw a nice six-membered ring. Don't put a circle in it. Cyclohexane so far. That's about as far as we've gotten. Okay, then right off of here, draw another six-membered ring attached to the first six-membered ring. Right there on the side. That's your second six-membered ring. Now, we would say these are fused six-membered rings. What do I mean is these two carbons in the middle right here there's not four carbons there. There's only two carbons. This carbon is in this ring, and this carbon is in this ring. Okay? So they're fusing those rings together right there. Okay, next. Draw a six-membered ring right up there. Right at that position. Exactly like that. We now have three fused six-membered rings. And then finally, just draw a straight line right there and put a roof on it. Put a little five-membered ring coming off of the side of that last ring you just drew. And this is what I will refer to as the steroid nucleus. All right, this is the general structure that you will see at the center of all the steroids. There's going to be a lot of variety that comes into here, but you're going to be able to see, and for the most part, this structure in most all of these steroids that we talk about right now. So that's the steroid nucleus, and I expect you to be able to draw that. All right, if you can see, that is this. This is a little prettier, but that's basically what I'm drawing right there, is 1, 2, 3 six-membered rings like that, and a five-membered ring in that position with a total of 17 carbons. So there's carbon 1, 2, 3, 4. Here's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. You can see carbons 5 and 10 are in both of these rings. 8 and 9 are in both of these rings. 13 and 14 are in both of those rings. That's your steroid nucleus. If I were to actually try to draw out the structural formula, not a line diagram of it, but a structural formula, I'd have something like that. There's your 17 carbons. That's the carbon skeleton of the steroid nucleus. I got this molecule over here because this is the building block. This is what the body would use to construct that ring structure, isoprene. It's got this thing here with 2 double bonds in it, and it can start polymerizing these on one another and starting to form these bonds, these rings. It's nonpolar. It is soluble in nonpolar solvents. It can be stored in the fat tissue. Okay. All right. What are some steroids? And yeah, kind of know. Yeah, I could have a question. Which of the following are steroids? Five things there, and you'd have to pick out the ones that are steroids, or the one that is a steroid and the others that are not. So some real common steroids. Cholesterol. Cholesterol is a steroid. Here it is. Now here's your steroid nucleus, and what do we got? We've got an OH over here. We've got a double bond over here, a methyl group, and some other nonpolar group here, and there's cholesterol. Even though this doesn't look like a house, that's still a 5-membered ring. 1, 2, 3, 4, 5. So, okay, so that's cholesterol. Precursor. This is the molecule that the body's using to make the other steroids. The male and female sex hormones are steroids. So they're being, cholesterol is one of the precursors, one of the starting materials to make those. Here's a little flow diagram showing that. So starting with cholesterol, then you pregnenolone, progesterone. From progesterone, you can make cortisol, testosterone. This is interesting. Here are the 2 female hormones. The male hormone, in between here, you've got the progesterone, which is the precursor to testosterone, which is the precursor to estradiol. Other steroids in here. Aldosterone regulates the reabsorption of all these electrolytes in the kidneys. So this is important for the body to determine, do we want to keep this sodium? Do we want to excrete this sodium? Are we deficient in sodium? Is the body got too much sodium? And so it's regulating that. Reabsorb it, excrete it, what do we do with it? So this is critical to that process in the body. Okay, let's look at some of those molecules. So cholesterol up here on the left. All right, so testosterone. There's your steroid nucleus. You got a ketone, got a double bond, methyl groups, and alcohol. Estradiol. Now notice estradiol, you got an aromatic ring right there. That's an aromatic ring. You got conjugated double bonds around in that first ring, and then just regular saturated rings. But yeah, we've clipped off a methyl group. We have the alcohol, the methyl, an aromatic ring, and instead of an ester, or a ketone, we have an alcohol. Phenol group there. Cortisol, aldosterone. Notice here, this is vitamin D3. Vitamin D3, and you don't see this four-membered ring, but if you, let's see, what would you do? If you were to clip this bond right here, it would unravel. This thing here, you got 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. If you broke that bond right there in that six-membered ring, you would end up with this. So this is a steroid vitamin D3, very important one. All right, even though you don't see the steroid nucleus intact, it is very similar. The steroids are the precursor to vitamin D3. Okay, you don't, on the homework, I may have you draw some of these things, but just know they're all steroids. Know these are represented, or these are in the class of steroids, and be able to draw the steroid nucleus, but I won't expect you to memorize all these steroids and their exact structures. All right, just again, so there's estradiol again, pointing out the aromaticity in there. Estrone, progesterone, testosterone again. Yeah, estrogens, androgens, progestins, adrenocorticoids, mineral corticoids for regulation of this reabsorption of electrolytes. Okay, great. We're doing great. Prostaglandins, some of the other things that are mentioned in chapter 17. I would suggest you skim over that stuff, and that other fatty acid that I mentioned, a really long-chained one. It's a precursor to, I think, prostaglandins and some of the other lipids. Skim over some of that stuff. The last key topic in chapter 17 is to talk about cell membrane structure and just kind of appreciate what's going into the cell membrane. Okay, you ready for that? And then we'll see how we want to handle the homework. Cell structure. Okay, two major types of cells. Single cells, like for bacteria, prokaryotic cells, and eukaryotic cells. Now, let me just pause for a moment and comment. So we got bacteria. They have a certain kind of cell structure. And then animals and human beings, many-celled animals, have a more complex cell structure. This difference in cell structure is the basis for a whole lot of what's the word? I'm choking on the word here. when you go antibiotics. Antibiotics. There you go. Antibiotics. It's a pretty simple term. I was just on them here a little bit ago. All right? So you take an antibiotic. What's it trying to do? It's trying to kill bacteria. It's trying not to kill you. All right? You don't take an antibiotic to kill you. You're trying to kill the bacteria that may be causing you some difficulties. And the antibiotics, this is why cell membrane research is elevated to such a high level, because the pharmaceutical companies are really trying to target the bacterial cell membrane and not target your cell membrane. Okay, so that they're actually trying to build a molecule that will compromise the cell membrane of bacteria and not hurt your cells. That's one class. That's the broadest class of antibiotics. They're targeting cell membranes of bacteria. So that's one thing to keep in mind. The other more complicated class of antibiotics target the replication process of the bacteria. So it's actually going after the DNA and trying to penetrate the cell and penetrate the nucleus and interfere with the reproducibility of the replication of that bacteria. And that is a stronger antibiotic and a little bit more, you got to be a little bit more careful with those antibiotics because they are targeting the replication process of the cell. The first broad one is targeting the cell membranes. Okay, so these are more complex. So what do these cell membranes look like? All right, the basic building block is a lipid bilayer. A lipid bilayer. All right, and what we've got here really is a phosphoglyceride in the ordinary cell of your body. We've got two layers of phosphoglycerides. This is your hydrophilic end of the molecule. This is your hydrophobic tails coming off of here, a fatty acid and two fatty acids. And the fatty acids orient towards one another, and the hydrophilic heads on them are on opposite sides of that bilayer. So keep in mind that on one side of this is the outside of the cell, and on the other side of this is inside the cell. Cell starts with a C. All right? Sounds like an S. All right, so that's inside, this is outside. And basically what it is, it's a doorway. This is you got to pass through this lipid bilayer to get in or out of that cell. This is the sheath around the whole cell. Lipid bilayer. All right, now, it's more complicated than that. Here's your lipid bilayer, all this blue stuff. It's your lipid bilayer. Well, stuff does have to get in and stuff does have to get out of that cell. How does it do that? Well, there are things embedded in the cell membrane like this, which would be a complicated protein. This would be a protein molecule with a particular shape, with a particular channel going through it for the passage of something. For example, sodium and potassium ions. Or there might be another protein for the passage of calcium and magnesium ions. To allow calcium to come in or magnesium to go out or vice versa. There's cholesterol embedded in the cell membrane. Here's a glycolipid. There's just all kinds of things. Another different protein molecule here. embedded in this lipid bilayer. So it's a complicated mosaic of stuff that that controls access to the cell and protects the cell from foreign bodies or the infiltration of something foreign into the cell. So there's a bunch of different things on here that would signal that hey, this is friend, this is foe, you know, don't let this in, go get it, attack it, destroy it, whatever. There's stuff going on the outside of this cell membrane to sense what is coming and what's needed and where to get it to. So we talk about active transport. Diffusion of gases, diffusion of ions in a solution is passive transport. Things move from high concentration to low naturally. But this is going to actively transport things in, even if they're low concentration out here. They're going to get them and get them into the cell if needed, so that would be actively transported in and out of the cell. The membrane structure is 60% lipids, 40% proteins. The typical cell, phosphoglycerides, the nerve cell, sphingolipids, sphingomyelin. Okay, and that covers chapter 17. Any questions?
So we don't really have to know about the uterine
No. No, not a lot. The eicosanoids, something like that. Yeah. Well, the prostaglandins, eicosanoids, yeah, just skim over that in the chapter. Be aware of them. I'm not going to dwell on them here.